Okay. Oh, okay, very cool. Share screen. Screen on share. Starting there and starting at the beginning. Is my screen in order?
Yes, your screen is in order and you're live on YouTube as well.
Perfect, thank you. Just one moment. And it's 8 o'clock. Good morning, ladies and gentlemen. Hope everybody is well today. Welcome to lesson number 3 since the start of lockdown on Maths grade 11. Just a reminder, I'm your teacher today, Miss Shabalala. As I mentioned, we are going through trigonometry at the moment. We are on day 3 of our trigonometry classes, and today I'd like to welcome all those that haven't been here before, for whom this is their first class, hoping you can catch up. And to those who've been here before, you guys know the rules of engagement. Let's go. Right. Our rules of engagement remain unchanged. Our rules of engagement are centered around how we will all treat each other. And sorry guys, there we go. Our rules of engagement are centered around how we will all treat each other and how we'll all take care of each other. We are here to all learn, and I'm hoping that we are all here to experience maths differently and positively. All right. So our rules, ladies and gents, please respect everyone because we are all here to learn. But 2, there's no such thing as a dumb question, so please ask away. Some of you have become familiar with the rules because we do revisit these rules every single day, but I'm going to need you guys to always bear with me because some people are new and today is the first time that they will be seeing the rules. Okay? Our rule number 3, please keep your microphones on mute. If you have a question, please raise your hand, and when you're unmuted, you're welcome to ask your question. Alternatively, you can just send your question into the chat box. Please make sure your question is concise and to the point. Right? We will not tolerate vulgarity. As I mentioned, we're all here to respect each other and to learn. And centered around respect is how you communicate. Okay? And lastly, please do not take the opportunity to learn from someone else. This is a platform that we are all going to work on. Given our prevailing lockdown circumstances, we're here to make the most of it, the best of it, to learn as much as we can, such that when we do go back to school, things are much more easier or manageable here and there. Right. So for today's lesson number 1, we are going to go through yesterday's practice questions in depth. I gave you guys 5 practice questions yesterday. We will be working through those questions as part of our class before we begin on our reduction formula. So today we are going through those questions, and then we're just going to quickly have a revisit or a revision of your Cartesian plane, the signs thereon, and the identities. From there, we're going to shoot straight into reduction formula for today. Reduction formula is a slightly lengthy topic, so we will be doing it over the course of a few lessons. Right, so now we will go through yesterday's practice examples in depth. Okay, this was yesterday's first example that we went through. Again, guys, given that this is a maths class and comprehension is what matters the most, I'd like to please ask you guys to please interact with me. Your interaction is an indication that you are following, that you are understanding, and also your interaction allows me to correct if there's any mistakes, to clarify if there's anyone not understanding, and so I can ensure that we are all keeping up with the lesson. So our first, our first proof of the day. So that's the other thing I'd like to highlight, the manner in which the question gets asked, right? Here I have said, prove the following. The moment a question says to you, prove the following or prove that, the question is basically saying to you, this is correct. The debate is not about whether it's correct or not. This is correct. Just show me how we get from left-hand side to right-hand side, right? This is one way of asking this question, prove the following. The other way being solve the equation or something like that, which is unlikely. Then you sometimes get a question that says, disprove the following. So this entire statement has changed and you've added this in there. When your question says disprove the following, all that means is that they've given you, again, an equation, and they are definitely saying to you, this is wrong. When that happens, your responsibility is to prove that the one side is different from the other side. As I've mentioned in my 2 previous classes, the aim is always to try as far as possible to simplify your expressions. And so if you find cods and tangents in both the left and the right, you should simplify that to bring us to the lowest degree, whether you are proving a false or you are proving a true. You are proving something true, right? Is there anyone who is willing and would like to go through with me as to how we got to proving this here practice example? As I'd mentioned, guys, this is one of those days where your interaction is quite important. On days where our point of
Jerusha Govender raised her hand.
Okay. Jerusha, thank you so much for being willing to assist me. You and I are going to go through this. You'll take me how you reasoned it. We'll look at how I reasoned it, if it's any different, and we'll take it from there. So what I appreciate also, guys, about interactions is that it's also an opportunity for me to learn the different ways in which to do one thing. Yes, I know there are a few ways, but there's always a chance to learn. So Jerusha, are you ready for me? Are you ready for us to go through how you would have solved this?
Apologies, it seems she doesn't have a microphone, so she corrected the error.
Oh, so we're going to continue without her. Okay, Jerusha unfortunately does not have a microphone, so we will go through this step by step. Is there anybody else who would like to try to solve here this equation with me? If there's a way as well, guys, please, in the live chat, in the chat box, I would like you guys to please also post your methods or your steps that you went about this to be able to share with everyone. So I'd said, because this is a learning opportunity for all of us, also a way to test how we can think differently, how we can see things differently, and just to see how different schools of thought still do lead to the same conclusion when we're talking maths. Right, so I see there are no takers for going through this example. I will begin the example. I'll take it line by line. I'll follow through step by step. And if there's any questions, please raise your hand. Please stop me. Please ask. Because as I had said, we have 5 practice questions to get through, after which we need to begin today's work. All right. Okay. So, as I had said, the moment you are being asked to prove anything, your purpose is to prove that the left-hand side equals the right-hand side. And so there's different, guys, emphasis, there's different ways of expressing this. Some people don't even write left hand and right hand. Some people just go ahead and write what they need to. Some people write it underneath each other. That's not the fuss. The fuss is the actual work. The fact that we express things differently is merely a consequence of the fact that we are people, we are different, and we do come from different backgrounds. Okay, so here, this one I found to be, I don't know about you guys, but I found this one to be a little bit tricky, because as I'm the one who always says to you guys, try to express your expressions as basically as possible, at as simple a level as possible, where you are referring to sine and to cos. And when you look at these two sides, both of them actually refer to sine and to cos. And also when we're talking denominator, how do you get cos on the other side, or how do you get sine on the other side? So what I have done was, for my first step, I took my original fraction and I multiplied it by 1. Multiplying by 1, I multiplied by 1 over 1 plus sine A over 1 plus sine A. What was the purpose of this? The purpose of this was to add a denominator that would look the same. It was to add a common factor in the denominator that would look similar to the right. The other option that you could have had was actually to solve for the right side, where you would multiply by 1 minus sine A over 1 minus sine A. And so yes, this was my first step. I hope everybody understands why I did it, but ultimately, in substance, we merely multiplied by 1. And so we did not change the meaning of the equation. Next up, I solved. So what I did was I found my lowest common, I multiplied my first formula with my second formula, my denominators and my numerators. I think you guys might have caught on quickly that the top one it looks a lot like your factorization formula. And so 1 times 1 is 1, minus sine A times 1 is minus sine A. 1 times sine A is sine A, and our minus sine A times plus sine A gives you a negative sine squared A. And that's how we got to that next step. From here, you can basically see the plus sine A, the minus sine A cancel each other out, and we found ourselves left with 1 minus sine squared A over cos A times 1 plus sine A. Everybody happy so far? Does anyone recognize anything that we learned yesterday from this point? I hear alarm bells, guys. This up here is one of our Pythagorean identities. And when we solve them for that, when we solve for our Pythagorean identity, we get ourselves a cos squared A. 1 minus sine squared A is equal to cos squared A. That comes from yesterday's Pythagorean identity that says sine squared A plus cos squared A is equal to 1. Right? And there we have our denominator that remains unchanged. From here on out, so we can all see how you are able to divide 1 cos against 1 cos. So you can cancel out, some institutions would call it. So here we have cancelled out 1 cos A against 1 cos A, and we have a cos A remaining. When we express that, how does it look? It looks a little like this. Cos A over 1 plus sine A. And here, ladies and gentlemen, our left-hand side and our right-hand side are equal. And we have proved correct the equation that has been given to us. Is everyone happy? Are there any questions? please raise your hand, please ask in the chat box, and I will respond accordingly. There seem not to be any questions, and so students. Right, if there seem not to be any questions, and so we'll move on to our second practice example from yesterday. Yesterday's second practice example was to prove cos squared b times tan squared b is equal to 1 minus cos squared b. This one seems relatively easy. Are there any takers who are willing to go through this one with me? No takers? No. Okay, that's all right. No takers yet. So, as I previously mentioned, one of my number one rules or rule of thumbs for trigonometry is, where necessary, where possible, try to simplify your tan in terms of sine and cos. So basically what I'm saying to you is try to always apply your quotient identities, which we learned yesterday. Always also, when you are solving for equations, look at what you deem to be the simpler side and try to make the less simple side reflect the simpler side. You don't always have to solve both sides of an equation, but sometimes you do. In this particular instance, I'm of the opinion that we don't need to solve both sides of the equation. But as I've always said, there's always more than one way to do this. There's always more than one view of certain things. And so, as I would like, we should teach each other, leave our responses in the chat space and see from there. Right. So from here, my first thought was to basically convert my tan squared beta into a quotient function, a simplified function in terms of sine and cos. And that for me meant I converted tan squared beta to sine squared beta divided by cos squared beta. And then I kept my cos squared beta. From here on out, doesn't get any simpler. Your cos squared betas both cancel each other out because it's the equivalent of having to multiply by 1. And so those would cancel each other out. And you then are left with sine squared beta. When we go back again to yesterday's Pythagorean identities, this is identity number 1 from yesterday, where sine squared beta can be expressed as 1 minus cos squared beta. Or alternatively, you could have solved for minus cos squared beta and simplified it to sine squared beta. In which case, then your left-hand side, ladies and gentlemen, is equal to your right-hand side. Any questions, any comments, any confusions, anyone needing any clarity? Okay, I'll take it that we're all good then. I'm going to move on to practice example number 3. Why? Somebody's asked me, why do I always solve the left-hand side first? So there is absolutely nothing wrong with solving the right-hand side. I've just found that so far in my questions, the left-hand side seems like the more complex side, and so that is the side I'm looking to simplify. And some people would have, as I did in this instance, you would have simplified the right-hand side first and taken it to sine squared beta, but that would have meant you'd have to resolve this side as well. So you're more than welcome, guys, to look at the right-hand side and solve that first. Absolutely nothing wrong with that. My method that I personally suggest is to say to you, always try to make the more complex looking side resemble the simpler side. Hoping that makes sense, hoping that you are answered, sir. Right. Okay, then now this, guys, is, I want to say to you, the ultimate fave. It's when you see this in the paper, you know, there you have 2 marks, bam, 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 with barely any effort, hoping that we're all on the same page about this. Let's do it. Any takers? Anybody willing to assist? Guys, this one is quite easy. So easy. Surely somebody's going to assist. Somebody, anybody. Okay, fine, guys. We'll go through this one. As you can see, it looks a lot like your factorization as well, where you have 2 brackets and you're multiplying your expressions in your brackets. So again, in this instance, I'm of the opinion that the left-hand side looks a bit more complicated than your right-hand side. And so I will be solving the left-hand side first. Let's go. Here, ladies and gentlemen, is how my next step looks. I think we can all agree that I made an error in terms of signage. This should be a minus because these two should cancel each other out, because we have here a 1 times 1, which gives you this one. Then we have a cos times 1, which gives you the positive cos. Then when we move on here, we need to account for the negative cos, guys. And so the flow is the 1 times the 1 cos. Sorry, that's how you get to it, 1 times the minus cos. There is my fault. This should be a negative, such that this plus and this minus will cancel each other out, leaving us with a 1 minus cos squared. And again, when we have 1 minus cos squared, we go back to our quotient, our Pythagorean identities. We could decide to stop here for the left-hand side and then go back and convert this into a cos expression by virtue of your Pythagorean identity. I opted to simplify the side to sine squared A. And then, ladies and gentlemen, we have a left-hand side that equals a right-hand side. Any questions, any takers, any opinions? Okay, I'll take it that we're all good, and we'll move on to example number 4. Okay, so I've been asked to go back and do the right-hand side one for number 1. In the interest of time, can I just finish these 5 and then I'll go back to give you guys a view of what the right-hand side for number 1 would look like. Okay. Then, guys, here's this one. It's got a cot in it. I nearly screamed when I saw a cot in it. So we have cot squared alpha, sine alpha cos alpha, plus cos alpha sine alpha equal to cot alpha. As I had said, I'm basically telling you that this is correct, and I'm saying to you, prove to me how this is correct. So again, we have our standard left-hand side equaling our right-hand side, and we will be proving for that. Is anybody here to assist me? Would anybody like to assist me with this one? Are there any takers for this one? Yes, no, 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 no. I see there are no takers. Okay, guys, once again, in this particular case, you could simplify your right-hand side to be a reflection of sine and cos. And you remember cot is the inverse of tan. It is the reciprocal of tan. And with tan being sine over cos, you know that cot is then cos over sine. So a simplified version of your right-hand side would have said cos alpha divided by sine alpha. Again, I have opted to work with the left-hand side. On the left-hand side, I have identified a common denominator in between my addition sign. There is My common denominator is sine alpha cos alpha. Taken that out, and I've left in my bracket from a factorization perspective, I've left cot squared alpha plus 1. Ding, 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 alarm bells should go off again, because what we now have, ladies and gentlemen, we have an identity, one of our Pythagorean identities from yesterday, right? And that Pythagorean identity says cot squared plus 1 is equal to sec squared. So this, ladies and gentlemen, sincere apologies, should be an exponential 2, not a big 2. This should be an exponential 2 for a square. Right. So here, our next level, we're at sine alpha cos alpha, and in our bracket, we have sec squared alpha. We're going to simplify our sec squared alpha. Always said, try to bring the reciprocals back to the basics. Simplify that to the inverse of sine as it is, and that is what you have. So immediately, you can all see, I'm sure, that you can cancel this sign out against one of the signs in here, so that you are left with a sign, right, like that. And so now, your expression that you have remaining is actually cos times 1 over sine alpha. You have that. You can simply write it as cos alpha over sine alpha, which, as I mentioned, is actually equal to cot. I just went and said the left-hand side is equal to cot. You had the option of eliminating this step over here. You could have left out this step over here. You could have just come in here and you could have said cos of alpha over the sine of alpha. And in both instances, ladies and gentlemen, your left-hand side and your right-hand side would be equal. Everybody happy with that? I'll take it when there's no comment that it means that everybody is happy with that. I have a question. Somebody asked me, how did I get sick? Okay. How did I get sick, guys? This is one of the quotient our Pythagorean identities that we worked on yesterday. So how we've gone about this to date, we started with the reciprocal identities, and then we've looked at quotient identities, and we've looked at Pythagorean identities. Unfortunately, because of time, I can't take you through the entire steps of how we went about this, but if you can look on the drive, the links you'll receive the links for that. You look on the drive and you look at our lesson 2. I've proven to you how cot squared plus 1 turns into sec squared plus 1. But in summary for now, I'll say to you, it is one of our Pythagorean identities. Right. Then, oh, guys, actually, I see the question. The fact is, the error on my part is, it is not sec, it is cosec. Oh, well, I seem to have made the correct conclusion around it being centered around sine, but it's actually cosec, not sec. Sincere apologies for that. But my response says that cosec comes from yesterday's identity. Sincere apologies for that, guys. Absolutely went over my head. But yes, this is how you resolve this. Next up, we have sine squared plus cos squared plus tan squared is equal to 1 over cos squared A. Any takers for this one? To Umulema, my previous lesson is not on YouTube, but it is available on African Geeks. You guys, I'll send out the links. So on YouTube, I'll put out whatever links that I can to avail this stuff to you guys. Also, you can contact me. I'll give my contact details again at the end of the lesson. All right. Okay. So with this here formula, what I've done first is I have used our Pythagorean identity to turn sine into cos. Right. And so here we said sine squared A is actually the same as 1 minus cos squared A. And then I've also taken my tan and expressed it in a quotient form as sine squared A over cos squared A. And so as you can see now, the singing theme in our information is cos, and your right-hand side is based on cos. There we go. And so I've simplified this because this minus cos squared A and this plus cos squared A will cancel each other out. We are left with a 1 plus sine squared A over cos squared A. Remember, guys, when we are adding fractions, we find the lowest common denominator. In this instance, I have taken my 1 and expressed it as a cos squared A over cos squared A. And so now we have a low common denominator, and we can express our answer as cos squared A plus sine squared A over cos squared A. The moment we do that, ding, 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 alarm bells. Here we have our first Pythagorean identity that says cos squared A plus sine squared A is equal to 1. And we have our denominator. And here, ladies and gentlemen, we have proven the left-hand side to equal the right-hand side. Hoping everybody's happy. Any questions before we move to our last practice example? Okay, it seems that everyone is happy, and we will move on to our last practice example. Oh, that was our last practice example. Oh, okay, guys, great. We're done with our practice examples, and we will just quickly be looking at trigonometry on a Cartesian plane. So while I take note of the time and I'm cognizant of the time, it looks to me today like somebody asked what happened to the tan squared A in the previous slide. Let me just go back to that. Your tan squared A has been converted to, has been expressed quotiently as your sine squared A over your cos squared A. That's what happened. Hoping that answers your question. Right. Trigonometry on a Cartesian plane. So today we are going to really do that part, that intro, and we will continue from there tomorrow. I guess the purpose of today is just for us to quickly understand your positives and your negatives, or quickly remember, as is grade 10 work, positives and negatives, so that tomorrow we're going to hit the ground running with our reduction formula. Guys, I'd appreciate your feedback a lot. I know that schools work at different paces and different levels. And so I don't know how far you guys have gotten in terms of grade 10 reduction formula. I don't want to be stating the absolute fundamentals starting from scratch unless there is a need to. So I'm depending on your guys' consensus around where we are. If I don't really receive feedback around that, I'll take it that I'm starting at grade 11 level from tomorrow. I'll take it that you know that your sine 90 plus x is equal to sine 90 and. So here we have our Cartesian plane that's got 4 quadrants. We know that our first quadrant is the quadrant that we grew up seeing. We've always seen it as being the x-axis against the y-axis. In this space here, everything is a positive. Your x values are positives and your y values are positives. Then you have our second quadrant, where it is basically an extension of the x-axis, and you are now able to see negative x values, while all your y values remain positive. Quadrant number 3 is made up of your negative x-axis and your negative y-axis. And quadrant number 4 as well is made up of a negative y-axis as well as a positive y-axis. This is quite simple. I think this is what comes from the basics of what we've grown up with, where we know that in the first quadrant and the fourth quadrant, x is always positive and x is negative in the fourth quadrant, etc., etc. I'm going to take for granted, guys, that we've been doing this. We all know it, we're aware. And so I don't need to go through a detail of explaining how we arrive at that information. So here, guys, oh, my picture actually looks blurry when extended. Apologies for that. Didn't seem blurry when I was working on a normal screen. So here, is everyone happy that, let's assume that we are working with angle beta. Is everybody happy that in quadrant 1, angle beta is less than 90 degrees? Or what I'm saying is we can basically rename angle, quadrant 1, and say it's beta less than 90 degrees. And then the 90-degree angle is sitting on its own. Then we have quadrant 2, where beta is more than 90 degrees, because at this point we've passed the 90, but it's less than 180 degrees. That's our quadrant 2. Quadrant 3, in quadrant 3, any angles in quadrant 3, we have beta being more than 180, less than 270, and quadrant 4, more than 270, less than 380. Remember, guys, you could literally, this, as you can see, let me do this, let me just use a pen to say to you, you could very well view this as your protractor, and these are all the angles of your protractor. This is your origin point. This looks basically like a protractor. So this is where you would find your 30 degrees, and this is where you would find your 150 degrees, for example. Now, everybody's happy with that. You can take your protractor and flip it around completely, and we know that this side, we have what we call reflex angles. And this is almost like you're saying everything in your protractor up to here is 180. When you turn your protractor this way, when you start adding whatever, 180 plus whatever number is on your protractor. Hoping that makes sense. Hoping everyone is on the same page about that. Guys, then we look at our positives and our negatives. Do you guys remember from last year the little phrase that says a smart trigonometry class? That, guys, is how we know which identities are positive in which quadrants. So in quadrant 1, all identities are positive. Quadrant 2, your sign identities are positive. Quadrant 3, your tan identities are positive. And in quadrant 4, your cos identities are positive. Remember how I explained how you basically explain, you could basically substitute the name quadrant 1 with beta being wrong sign, guys. With beta being less than 90. Where's my pen? Yeah, beta being less than 90. And how else can you express that fact? You can say that beta is equal to 90 degrees minus x. X ranging from anything between 1 and 89. I hope we all agree. Does everybody agree with that notion? And then when we move on to quadrant 2, we can express quadrant 2. We can say that the beta in quadrant 2 is actually more than 90, less than 180, as we've previously done. And we know that we can express quadrant 2 as 180 degrees minus x. This is reduction formulas. Now we're talking reduction formulas, how you could reduce this kind of formula, right? And then, don't know how many of you know, but you can obviously see that you could have also said beta is actually equal to 90 plus x. So the 90 plus x is not as common as the 180 minus x, but it's a good to know, and it does appear every now and then. And just a reminder, all your sign identities are positive in here. Then we have tan. We know we can replace our tan by saying that it's between your beta, in your tan, in your third quadrant, your beta is between 180 and 270. And again, we can express that in terms of saying 180 plus x, which is the more common one. But tricky, every now and then you get your 270 minus x. Just be on the lookout. Those like to be special, but they do appear here and there. It literally has the same implication, right? Then we have our quadrant 4, where our angle is between 270 and 360. In that space, we know we always find that, and we see it as 360 minus x. Now, I know you could say 360 minus 190, then that throws you in the tangent. But we're basically, I'm going to say we're going to cap the x to the numbers on a protractor. So the x would be up to 180. But because, sorry, we've divided our Cartesian thing and separated in factors of, they call a factor, in multiples of 90, that's how you would stop at 90. And so, guys, our time for our lesson's almost up. These are so when we're talking about a reduction formula, we are basically saying we want to take your 90 plus theta, your 180 plus theta and the like, and we like to write them simply in terms of theta. So here's one example. Sine plus 180, sine of 180 plus theta is minus sine. Why is it minus? Because here 180 plus theta is in quadrant 3, and in quadrant 3 only 10 is positive, so your sine is negative. Here we have cos of 360 minus theta. In quadrant 4, cos is positive, and that's why it comes out as cos theta. Likely in quadrant 2, only sine is positive, so 10 is negative, and so that's why you have it as minus 10 theta. We're going to go into detail about this tomorrow, but this is basically the intro into this, right? So I've posted some helpful links with the slides. Always, as I had said, Siyavula has straightforward examples, the starting examples to get you into the groove, and then your Khan Academy has quizzes that I quite enjoy. I hope you would enjoy it too, right? What are we doing tomorrow? We're continuing on our reduction formula. The main focus from here on out for the next 2 lessons is going to be your working examples, and we're going to do practice examples, because as I've said, guys, I've taken for granted that you have quite an idea of how reduction formulas work. We are here to build on that knowledge, to strengthen, to show you the funnies, and to take it to a more advanced level, right? Any questions, guys? Because we're out of time, I'll ask you to please contact me there on Twitter. My Twitter handle is @_Mbali. I'm happy to take your questions. You can DM me on there. And here we are. These are our details, guys. You can contact us, our STEM Lockdown School. These are all the social media platforms you can find us on. And I hope we've had a good lesson today, guys. As you know, as I tell you every day, keep the faith, keep strong. Everyone, we're doing well. We're almost there. We've got about 2 weeks left. Please take care of yourselves. Whatever religious practice you do, stay with that. Drink your water, protect yourselves, take care of your peace of mind. And I'll see you again tomorrow, guys. Have a good day, everyone. Bye.